I am so by day, I'm a software engineer for a very large ride sharing and food delivery company that will not be named since they don't use Rust. But in the nighttime, I do unfurl my cape and write some Rust. So what we're going to be talking about today is the Rust runtime, right? So firstly, I'm going to take a second to just lay out kind of the goals of this talk, and then we'll do a little bit of Q&A before diving into this. Firstly, we'll just work on understanding kind of like what a runtime is, since it's a little fuzzily defined, and I think it's kind of the source of a lot of misunderstanding when talking about Rust and Rust runtime. So we're going to spend a bunch of time reading some compiler code, right? So we're going to really get into like the depths of it and read some things that, like, frankly, I barely even understand. And we're going to discuss some trivia. We're going to work on understanding like how Rust bootstraps running programs. And most important to me, more than anything, is just give people an excuse to talk to me. I moved to New York a couple of months ago. Frankly, most of my time I spend sitting in front of my laptop in my tiny, tiny apartment, talking to people in California and India. And so, it'll be nice to actually meet some real live human beings and have an excuse to talk to folks. So, thank you. I appreciate it. Cool. So now, as I'm slowly getting used to the winters here because California has made me weak, let's go ahead and deal with that and get started. So the biggest thing they'll hear about Rust, the Rust runtime, is people will tell you on the internet and just everywhere, like, Rust doesn't have a runtime, right? Like, this is repeated over and over again. And what hopefully you will understand by the end of this talk is that this is flatly wrong. This talk will actually be relatively short because Rust's runtime is actually relatively short. It is exactly 150 lines of code. So we'll be going through those 150 lines. But before we kind of get into this, a question for the audience, for anybody who dares speak up. What is a runtime? Like, what is a language runtime? Please.
Something outside of the program you explicitly write that allows that program to run where you refer.
Beautiful. I couldn't have said it better myself. So yeah, so basically what it is the instructions that are kind of that are like provided with essentially your program, if it's compiled into it, or however, that you generally don't explicitly write, right? So you can think of a runtime as essentially kind of the abstraction layer that sits between the code that you are executing and the actual machine instructions, right? So oftentimes, like, people will say that a lot of languages don't have runtimes, right? Because when we do think of language runtimes, it's generally things that are a little more like heavyweight, right? We think of garbage collection in Java. We think of just-in-time compilation. We think of like essentially the V8 JavaScript runtime, right? Things like this, big, hefty, chunky things, right? And so oftentimes, when we think of languages that are kind of like, closer to the metal, Rust, C, C++, we think they're like, okay, yeah, this doesn't have a runtime. This is essentially just like sits essentially nestled against the curves of the machine and is just executing code straight up, right? But the reality is, any language above the abstraction level of assembly has some form of runtime to it, right? So what we're going to be doing is just exploring kind of like what that is, right? So primarily how we're going to be doing this is we're going to spend, frankly, like, I haven't really timed this, but the next 10, 15 minutes or so, just reading through a single file. So the entire Rust runtime is contained within, so if you go into like the main Rust source tree, it is under library/standard/source/rt.rs. If you want to go on your laptop and just read along through it right now, totally fine. You can find it right there. So let's go ahead and just kind of look at this file and see what this provides us, right? So firstly, there's just kind of the preamble here, right? So basically, as it states, this is providing the heap. We won't dive into the heap so much since it's very like system dependent. And this file makes the bold claim that this module will not exist and will disappear. This is frankly a lie. It's been around for 7 years. It continues to exist despite all of the Rust folks, specifically Alex Crichton's intense work to destroy it. So it somehow stays with us. So one of the first things that we actually see when we look into this, right, is we basically have just like a bunch of infrastructure provided to us for panicking, right? So basically, if for any, I'm sure most of you have run Rust programs. I'm sure that most of you, despite your best efforts and your programming wizardry, have hit panics, right? So these just provide the infrastructure to rewind, to basically rewind stacks and to essentially allow you to provide custom panic handlers. We won't delve too much into these since I didn't spend a whole lot of time reading them. But if you'd like to, they're there. So this is kind of like where things kind of get like a little strange. So when the Rust, so we have like a bunch of these macros that are essentially doing like panics, aborts, stuff that is already essentially provided to us by the Rust standard lib, right? And so when reading this, at least myself with my small mindedness, I was like, why is this here, right? So when the Rust standard library is actually being compiled, there is actually a directive provided to it. I think this is probably, I'm a Rust novice, so I don't know how much people know or don't know. But you can actually compile Rust without, essentially with a no core or no standard lib directive, right? So in this case, what we're running with is the absence of a standard library. You can also write stuff without a core, which is very interesting. But in this case, we don't have a lot of the stuff of the standard library available to us, right? So in this case, when we're actually bootstrapping the runtime, we have to define all of these custom panic functions and custom abort functions that essentially figure out, okay, where panic's being written to, where is everything being provided to us, and essentially provide lightweight implementations of these that are kind of threaded through the compiler and the standard lib itself, so that we don't have circulating dependencies within the standard lib, right? Nothing too sexy here, just a bunch of macros. So this is kind of where things start getting a little bit weird, right? So this is actually where the runtime itself is basically has its entry point, right? So how do we know essentially that this is the entry point, the part that runs before main itself? So we'll talk about, so specifically this is like defined by the lang item up at the top here, right? Which is a little, which we'll discuss kind of like a slide or two. But basically for now, we just need to understand that when you are running a Rust binary, right, you're not entering into main, right? Specifically, there is essentially an entry point that is defined by this lang equals start into which the binary and the runtime itself will enter for the bootstrapping process before main is ever essentially executed, right? And as we can see, main is provided as a function. And we also have, probably very familiar for folks who have written NEC and C++, unfamiliar for folks who have come from more higher-minded languages, but we have argc and argv, right? So argc, the number of arguments, command line arguments that are provided to our program, argv, essentially the string array, or the char star that is provided to the program. And in this case, like we look at this and it's like, oh God, like this, like what is this horror doing here? Like this should be banished. Like isn't the point of Rust to essentially banish this into the hinterlands? But actually, we'll see a little later that Rust actually does a little bit of work to take these raw pointers and do some work with them to provide them in a slightly more digestible fashion to us programmers. So the other thing that we can kind of see is that main itself is defined as a function that is that essentially returns a T which must satisfy this like process termination trait. and also has a static lifetime, so lives throughout the duration of the program execution, right? So if we look at the termination trait itself, termination is just very straightforward. It is something that has, it's an object that essentially has an exit code associated with it. In this case, this is just going to be an int32 exit code, and just implements this like report function that tells you, okay, here's the exit code that I'm essentially returning. And I believe the exit code itself is just, I think it's just, I want to say an I size. Yeah, I think it's just an I size. So that's pretty much it. Yeah, so that's pretty much all terminations are. And then we have kind of like this bit about a lang item. So lang items are really weird because they're, I think as one blog post that I read far too many times described it, lang items are essentially kind of like the special snowflakes within the Rust compiler. So specifically, there are pieces of code that, and essentially like functions that the Rust compiler needs to know about in order to execute code, but they can't, like, they're actually being provided and executed before the compiler itself is able to bootstrap, like, you know, these traits and like all of these things that we would expect here, right? So lang items are essentially this like enormous table within like the langitems.rs file that are just defined as basically strings that function as syntactic sugar for specifically the functions that they're going to be mapped to, right? So in this case, I don't think that start shows up here, which is unfortunate. I should have thought that. But basically what this is telling us is anything that is, any function that is decorated with a lang equals start lang item is essentially going to be defined as the entry point for a Rust program. Specifically, if you attempt compiling a Rust program without its standard lib and without its core, you can define your own entry points using this without ever having to write a main, right? The one requirement is that it does, for these lang items to be correctly applied to a specific function, or these functions have to satisfy essentially the function signature that is going to be defined within this lang item table. Specifically, your start function must provide the ability to take in some form of main function. It also has to take in essentially your argc and argvs. So now, for codegen purposes, we have like, you know, this like lang start function, which then proceeds to call, here we can see here, it then proceeds to just, you know, run a backtrace on this main, and the majority of the work is going to just be done in this like lang start internal, which we'll kind of read through here. So lang start internal it's generally fairly straightforward, but it does have a couple of bits of weirdness to it. So specifically, so main itself is going to be passed into this block right here, which I'll explain. This block is a little bit interesting, so I'll explain that in a second. But the arguments themselves, the argc and the argv, are actually going to be passed into init, right? And so when init is going to do is it's going to take your arguments and it's going to provide all the functionality to package up those arguments into the standard env-args interface that, like, I believe like any of you have worked with, right? So it essentially takes out all the nastiness of working with raw pointers and essentially just packages everything up. We can dig into so for a lot of this code, I'm aligning a lot of the details that lie under the surface of this, because if you actually look into what, for example, like sysinit does, it's like very heavily platform dependent. There is a completely different init function for like Windows, Unix, Darwin, etc., right? And the functions themselves are like dramatically different, and it will probably be another hour of talking about this. And it also provides for us the niceness of actually setting up essentially guards for all of our main thread stack, right? So what this is essentially going to do is it's just going to write up it's just going to write a piece of memory that's going to prevent this thread from overflowing its stack, right? Fairly straightforward, but for anyone who's written any C, this is actually like pretty nice. Yeah, and all it does is it spawns the main thread, and then it sets the stack guard on that thread. So this bit, okay, so like init itself is like fairly straightforward, right? Like we essentially have, for most of this, we have this like catch unwind block handler around these things. Catch unwind is just, I mean, all it exists to do is it catches any errors and unwinds like back to, essentially unwinds the stack to like the previous stack frame. Now, what's kind of interesting is like this this comment here and this code block right here with the rec code. So what is actually possible here is so specifically there is this issue right here that describes a situation that in which let's say if you're working with the standard outside the standard lib, or if you have a bug within your standard lib, when essentially your main is going to be called at some point, it's going to be like dropped, right? And so if you can actually force a panic within the drop without essentially this this like chunk of code right here to essentially catch the error and kind of like unwrap everything, unwrap the unwind itself. Prior to this actually existing, there was a possibility to actually unwind outside of the Rust runtime itself, right? So you could actually unwind to the stack frame that was calling the Rust program, right? So you could forcibly escape by just panicking on a drop. You could escape Rust itself, which I found kind of weird, right? So essentially we have this like bit of protection that we have provided around main execution, and then we have cleanup being called. Cleanup itself, fairly straightforward. All it really does is it's synchronized to be called exactly once and flushes all the buffers and essentially just cleans up. Insist.cleanup, for the most part, cleans up any like stack overflows. It's like very system dependent, but for the most part, just cleans up any parts of the stack that overflowed their bounds. So that's pretty much it. Cool. So that's actually it. Incredible. So now let's just think about what we got, right? Like, so Rust itself provides us with stack guards, provides us with like essentially some form of like overflow handling and overflow cleanup, provides us with panic handlers, a bunch of like platform dependent signal handling that happens when sys.init is called. And it provides a bunch of safe APIs around raw pointers, right? So a bunch of stuff that we didn't cover was essentially like very heavily was basically just kind of like functions that were being called kind of just under this this like core runtime file. But for the most part, if you like look into all that, it's essentially all like platform dependent implementations of things that you would otherwise have to handle directly in C. And that's really it, right? So when somebody actually tells you that like Rust doesn't have a runtime, I mean like it's very like minimal, right? In so much as that we, I can come up here like 15 minutes flat, run through it, knock it out, and for the most part, you have a rough understanding of what's going on, right? So, there is no garbage collection. There isn't, we don't have any jing, we don't have any of these fancy things, but for the most part, there is essentially a significant amount of machinery that exists in order to package up essentially raw C and Unix constructs and provide them to you within a simple, safe, and very digestible fashion. So that's pretty much it. So the only other thing I've remaining are essentially the credits. Two blog posts and a Stack Overflow post that I utilized for creating this. The Michael Dozy's blog is actually like pretty good, and if you really want to dive into laying items, the second blog post is gets a little gets really into the weeds. So yeah, but that's pretty much it. I will. Yeah, that's all. Happy to take any questions. A lot of my answers will 100% be I don't know because I'm not really that good at this language, but happy to be honest. Please.
If you do no standard, it leaves out this runtime, or?
Yeah. So if you're, so this is, given that this is part of the standard lib, you can actually leave out this runtime completely. I'm not sure if I have this. I can actually show you kind of like what things look like here. So this is essentially kind of like what things, an example of like code that doesn't actually have a runtime or the core available to it. Specifically, the weird thing here is like you actually have to implement sized, and copy, which the compiler depends on to like do anything. For the most part, like in your start, you you can't really like do anything, right? Because like you're essentially like going as this gentleman points out, you are in a benighted hellhole and you're really like completely on your own. But like you can absolutely like write stuff without any of these memory or safety guarantees if you just drop the core. So yeah. Yes.
Also, in a dilib, you would have no runtime as well. Is that accurate? Or like, I guess you're statically linking this with another language.
Well, so I mean, dynamic. So like, I'm guessing if you're providing like a C dilib, you're essentially. I think that you're like you have to essentially like wrap it in unsafe code, right? For the most part, I haven't worked with dynamic libraries in Rust a whole lot, but like I think that there are like I think you're going outside of the Rust runtime for a lot of these things. So I'm sure that like if you call like the C the C standard lib under the hood, right? Like you are getting some sort of runtime, but like I don't think that like. You are going outside of Rust code, right? So like you won't have like the Rust runtime per se available to you. So like yeah, I guess. Yeah. Please.
So like you said, so like this hellhole we was talking about here.
Please.
Is that because you used one of the sugary entry points, like you didn't go in with the main, and like what is that? What is that like what is not calling the main leave you without? Like why does it put you in hell?
Yeah, so so right here, so this gentleman in a very biased fashion is essentially for the most part like talking about all of the things, all the nicenesses they talk like deal with as far as Rust, right? So like all of the like safety guarantees that you get from the compiler, all of that, like that's put completely out the window, right? Like if you want to implement like print anything, right, you'll essentially have to write your own code to write raw bytes to the terminal. Right, like essentially, like here, it's 42 because you're on your own, and as somebody once put it, the 0th level of abstraction is God, and here you're talking to him. So yeah, cool. Anybody else, please?
So I was looking back at the at your init slide.
Mm-hmm.
So like maybe like 2/3 of the way down in the init function, they create a new thread.
Yeah.
Is this where they actually starting like our main function, like from like if you have the runtime and let's say you just written like a hello world program on like one of the last lines of it, will actually spawn the thread to run our main?
So this is that's actually a good question because I did not look into this for the most part. So I think. So I think that what this is. So I have to to answer you like with confidence. I would have to read the thread new source code, which I've not. My guess here is that what this is actually doing is getting the current existing main thread, right? So this isn't actually like spawning this, right? This is essentially getting the thread that is existing already, right? And setting like essentially a stack guard for the thread, right? So this isn't actually like running main itself. That comes a little later, but for the most part, like this is just doing the bootstrapping to like make sure that we don't have any stack overflows. Please.
Okay, so like, so I'm someone who like mostly uses just like React and JavaScript and
Sure.
like Go Python or whatever.
Sure.
So like, when would be like the time like for just be like, yo, I need Rust. Like,
Yeah.
like some realistic, like a realistic situation.
I honestly think that is a much deeper question than you could imagine. Yeah, no, that's entirely fair. No, I think it's entirely fair. Yeah, I think honestly, if you're a nerd, it's kind of the biggest thing. No, I think that there are. So I think that a lot of it. So I think in order to like really understand kind of what this brings to the table is you have to. You really have to like spend some time in like this benighted hellhole, as they talked about, right? So, so for the most part, like, I mean, when you need things like performance, right, to like be close to the machine itself, right? Like, I work mostly on like cluster executors, right, and cluster schedulers, right? Like things that essentially take like thousands of containers and like place them various places. You know, I would like to say that I work on Kubernetes, but I don't even work on that. Like most of my time is like spent like tending to Mesos clusters, right? And so the story that I like to tell is that totally didn't happen at work. Is at one point we had a bunch of Mesos executors that essentially like would just like so they're like they're executing a read system call, right? They're just trying to read some data, and they just stopped. Like every like 2 weeks, like, actually no, it was like every like 2 days we would just have a random server just stop executing and just like pause, right? And it would just sit there and we had no idea why. And I spent about 4 months writing BPF to try and figure out why this was happening. And it turns out that somebody was just overriding the standard in file descriptor, right? So when you're essentially like, when you are working that close to a machine, for the most part, like, you know, we have had men far older than I provide us with C and C++, honestly C mostly, to interact with the machine in such a way. C is a cruel mistress, and this is a less cruel mistress. That's pretty much it. Yeah. Cool. Yes.
So, like on this slide with like the thread guard that comes up with the thread stack and workflow. So, is something like this getting called every time you spawn like a new thread of your own?
I believe it's I think it's probably. I don't like. I can't tell you for sure. I haven't read like Stack's like core threading library. My guess would be yes, but at least right here, like, you know, at least in your main thread, yes. So probably, yes. Please.
Sorry, this just seems like an
Saga?
anecdote, but it looks like it's writing metadata into thread level.
Yes, that's correct.
Does that make sense? I don't know really, but that's what it looks like. Makes sense.
Yeah. I don't know. Please.
In the part where it called like start internal, it passed a closure as a dynamic trait there, and made
Yes.
like this dynamic reference. Like, do we know if it could be an impl FN, which seems like a more modern way to do it, or if there's something like fundamentally that needs to pass to a trait object?
Yeah, so I mentioned at the beginning of this Q&A where there are going to be moments where I'm just going to say I have no idea. I think this is going to be one of those moments. Like, I really don't know. I think that you've escaped the boundaries of my Rust knowledge. So talk to me in 6 months. I have no idea. Please.
I think they do that to save code size so that it's not copied into like start every time. And it's only called once, so it's not much of an update.
Perfect. Thank you. Yes. Thank you. I do appreciate folks who know more about this than I do. Anybody else?
I guess I'm just curious, in what kind of way would you like to see Rust be implemented? I guess, working with cloud infrastructure.
What do you mean as far as like, would I love for it to be bestowed upon me at work, or what are we talking?
I guess, yeah, a little bit of both. It seems like you like CLI tools and
Yeah.
I guess working with
Yeah, I mean, I guess, so in what ways would I like to see Rust implement? I mean, for the most part, like, I don't know. I think that there are a lot of things that I found that, I mean, I think for the most part, like I think especially when you're working with like, like a lot of Linux machines for a long time, you see all sorts of like various crazy, memory bugs and like security issues as a result of just like, frankly, like everything just being written in C. And I'm not really kind of the purist that is going to sit here and like re-implement the entire Linux kernel Rust. If you would like to do that, by all means, go ahead. But frankly, I think that there is a significant amount of tooling that that I think is that just having having high performance code for is very, very nice. So specific, I mean, even like the vast majority, actually, I've written Go pretty much professionally, exclusively for like years now, and Go's good. It does exactly what I need it to do, but for the most part, there are still things that come up as a result of having made certain choices, right? Such as like garbage collection, right? Like, great, you can hire engineers to like actually write it, right? Everybody loves Go, right? Because like you look at it and you're like, oh, and you write it. Rust not so much, but you kind of once you scale up to like a certain level, you do also find that like GC tuning Go is like not nearly as common as like doing it in Java, but like I've seen instances where like doing a bit of like automated GC tuning in Go will like save you like $30 million, right? So and at least right here, like having having minimal usage of minimizing both CPU and RAM usage, I think is like quite valuable. So I don't know. Honestly though, it's more interesting to me than writing Go. So like that's frankly like the thing that I see it most used for in my everyday life. So yeah, that's pretty much it. Please.
You mentioned Go. Go has channels for the concurrency mode, and then Rust has threads. How do you compare the two?
I mean, I think that in this case I wouldn't, right? Like threads are essentially just they're like methods of execution. Rust is channels are simply for message passing, right? Like I'm sure I haven't done a huge amount of like multi-thread stuff in Rust, but like I'm sure that they're right, working on Tokai.io, please. Yeah.
Rust comes in with threads like Go. I mean, Go probably can expose threads. I think you can get libc access.
Yeah.
Right. Rust actually has like futures, which are very similar to Go's green threads. And in fact, like the most popular runtime, Tokyo, literally like has used Go's runtime as it's like there's like I think there's parts in the code that literally like we stole this random constant from Go's runtime, and we don't know no one knows why it's there, but it works. But like they're very similar. The big differences between like Go and Rust would be like your garbage collection, the tooling, and then like straight up like language features like type system, things like generics and other aspects, and backing.
Yeah.
People backs Go pretty heavily.
Yeah, absolutely.
That changed.
Gentleman in the back.
You mentioned there was a lot of like platform specific code in certain like
Sure. Yeah, I mean, I'm sure we can try and like look at this. Honestly, I think we should just do it with, I'm happy to like sit down and like take a look at it with you. Honestly, trying to like parse all the system dependent code will probably take a while. So, but happy to sit down and actually take a look into it. I haven't looked at the WASM stuff specifically. For the most part, I just look at Linux and I see the face of the Lord. That's pretty much it. Yes, Andy, please.
So you mentioned that in the nose code, you don't get this full runtime. Like the example you showed was no core.
Yeah. Oh yeah, yeah. So specifically, yeah. So you have no. So there are like two levels, right? You have essentially like no standard lib, right? Which is your standard library is not available to you, right? No core means that like nothing is available to you, right? So essentially you have to specifically here in the example that we showed, right? You have to implement the size trait, right? You have to tell the compiler how to size like things. Right. So in this case, like you are, so I mean, even if you're using like a standard library, right, you are getting this essentially like chunk of runtime with it, right? Like you do have essentially like a specific entry point defined. You do have all these nice little things set up, right? You just don't necessarily get like, you know, like standard env or whatever, right? Like in this case, you have to like you are, you're just giving up more.
So on what level would the runtime be? Like, if you have no state, but you still have runtime? Or do you have to?
Yeah, so I mean, you have this. I think there's specifically, you would still have the runtime when you're like doing like no standard, like so. Yeah. In here, so yeah, in here, I believe that if you're actually calling like loads your file with like no standard, right, you would still be getting this runtime along with it, right? You just wouldn't be getting the standard lib. No core is, you know, that's the proposition we're dealing with here, and that's slightly gnarlier.
Like you're writing an operating system and you have to write your own heap.
Yes.
And nodes would be like I'm running on an embedded device that has a very, very limited feature set that may not have a heap or may have specific requirements.
Yeah.
So that's the big.
I think that's an excellent explanation. Thank you. Yeah, that's I didn't say it better myself. So.
And there's a great blog series by Phil Oppenheimer on how to write an OS in Rust that will make you use macros. It's the only time I've ever used them, but
Yes.
it will teach you the pain. It's not as bad, but it's pretty bad.
Yeah, it's pretty gnarly. Let's do one more question. Anybody? Please go ahead.
What part of New York did you move to?
Upper West Side. Yeah, Upper West Side. Cool. I'll leave a Rust related question. Please.
So all this stuff around entering the domain makes me think about some of the C runtime stuff.
Sure.
GCC initializers and just shit that runs when your binary starts up.
Yeah.
How does that interact with Rust? Like if you bring in some C library that does that, where in the initialization of your process is this code related to that? So that's sort of the dynamic linter maybe? Or?
Yeah, I mean, so I think, so are we talking about like kind of this, also like kind of the dilib example where you're essentially like kind of bringing in like, you know, some new
I'm
code?
not familiar with Darwin, so I just know that there's like, you can insert certain segments into your binary that like on startup may run code.
Yeah, I'm honestly, this is like one of those things I'm not really sure about. Like, you know, I think that in any time, for the most part, like this runtime is just coming in any time that you're executing a Rust binary, right? You can actually, the one thing I didn't mention is you can actually like omit, like bypass this runtime for the most part, right? Like, so the whole initialization process, if you are actually calling like a Rust library from somewhere else, right? You can actually just bypass completely. Right, so I just imagine it's, I haven't done essentially the wizardry of like, you know, stuffing segments to places, but for the most part, I think that if you're calling a Rust binary, you're gonna be going through this whole rigmarole. Cool. All right, I'm going to stop talking now. Thank you so much. Much appreciated. Thank you.
All right, thank you. It was a fantastic talk. That was super cool. I think a couple of us are going to a bar after. Mendy, I think you're going to lead the way. But thanks, everyone, for coming again. I think we'll be back here in around a month or so. Again, if you would like to give a talk about learning Rust, please do. And we'll see you guys here next month. Thank you for coming.
Perfect. Thank you. Much appreciated. Yeah.
It was like 40